In this question, two relations f and g are given to you. You have to show that f is a function and g is not a function. Let's begin the solution of this question. First, let us consider the relation f. F of x is given by x square when 0 less than equal to x less than equal to 3 and f of x is equal to 3x when 3 less than equal to x less than equal to 10. Now we can observe that for each x belonging to the left closed and right open interval 0 to 3, f of x is equal to x square. Now we can also observe that for each x belonging to the left open right closed interval 3 to 10, f of x is equal to 3x. Thus we can see that f of x is uniquely defined for each x belonging to the union of left closed right open interval 0 to 3 and left open right closed interval 3 to 10. Now let us see whether f of x is uniquely defined at x is equal to 3. Now at x equal to 3, that is f of 3 will be equal to 3 square, that is equal to 9. Also f of 3 will be equal to 3x, that is 3 into 3, that is also equal to 9. So this implies f of 3 is uniquely defined because in both the cases we get the value of f of 3 as 9. Hence we can say that the relation f is a function. Now let us consider the relation g. G of x is given by x square such that 0 less than equal to x less than equal to 2 and 3x such that 2 less than equal to x less than equal to 10. We observe that for each x belonging to the left closed right open interval 0 to 2, g of x is equal to x square. Also we observe that for each x belonging to the left open right closed interval 2 to 10, g of x is equal to 3x. Thus we can say that g of x is uniquely defined for each x belonging to the union of the left closed right open interval 0 to 2 and left open right closed interval 2 to 10. Now let us see the value of g of x at x is equal to 2. That means g of 2 will be equal to 2 square, that is equal to 4. Also from this we can say g of 2 will be equal to 3 into 2, that is equal to 6. This is because 2 is included in both the intervals as we can see here. Thus we find that in the relation g given, two ordered pairs 2, 4 and 2, 6 exist having the same first element 2. Therefore, g of 2 is not uniquely defined. Hence we conclude that the relation g is not a function. So this completes the solution of this question. In this question, f of x is given as x square. You need to find the value of f of 1.1 minus f of 1 by 1.1 minus 1. Let's begin the solution of this question. F of x is given as x square. Therefore, f of 1.1 will be equal to 1.1 whole square, that is equal to 1.21. Also, f of 1 will be equal to 1 square, that is equal to 1. So, f of 1.1 minus f of 1 by 1.1 minus 1 will be equal to 1.21 minus 1 by 1.1 minus 1, that is equal to 0.21 by 0.1, which is equal to 21 by 10, which gives 2.1. Hence, the value of f of 1.1 minus f of 1 by 1.1 minus 1 is 2.1. So this completes the solution. In this question, we need to find the domain of the given function f of x is equal to x squared plus 2x plus 1 by x squared minus 8x plus 12. Let's begin the solution of this question. Here we have the given function x squared plus 2x plus 1 by x squared minus 8x plus 12. Now, for a given x belonging to the set of real numbers R, f of x is uniquely defined only when the denominator of this function, that is x squared minus 8x plus 12, is not equal to 0. Therefore, for domain of f of x, we must have x squared minus 8x plus 12 not equal to 0. This implies x squared minus 2x minus 6x plus 12 not equal to 0, which further implies x into x minus 2 minus 6 into x minus 2 is not equal to 0, which implies x minus 6 into x minus 2 is not equal to 0. This means x is not equal to 6 and x is not equal to 2. Hence, domain of f of x will be equal to the set of real numbers minus the set containing the elements 2 and 6. So this completes the solution of this question. In this question, a real function f is defined by f of x is equal to root over of x minus 1. You need to find the domain and range of this function. Let's begin the solution. So here we have the given function defined by f of x is equal to root over of x minus 1. So we need to find the domain of f first. Now, it is given that f of x is equal to root over of x minus 1. This means that x minus 1 is always greater than or equal to 0, or x is greater than or equal to 1. Therefore, we can say that f of x is uniquely defined for all x greater than or equal to 1. Hence, domain of f will be left closed right open interval 1 to infinity. It is left closed because x is greater than or equal to 1. That means 1 is included in this interval. Next, we are asked to find the range of f. Now, fx is equal to root over of x minus 1. Now, fx is given as root over of x minus 1. This means that fx is always greater than or equal to 0. Since root over of x minus 1 is always greater than or equal to 0. Hence, range of f of x is left closed right open interval 0 to infinity. It is left closed because f of x is always greater than or equal to 0. That means 0 is also included in this interval. So with this we come to the End of the solution of this question. In this question, we have a real function f defined by f of x is equal to mod of x minus 1. You need to find the domain and the range of this function. Let's begin the solution of this question. Now, before proceeding with the solution, let us understand what is modulus function. Mod x is given by x if x is greater than or equal to 0 and minus x if x is less than 0. That means a modulus function is always non-negative. Now the given function is f of x is equal to mod of x minus 1. This implies f of x is equal to x minus 1 when x minus 1 is greater than or equal to 0, or we can say x is greater than or equal to 1, and it is equal to 1 minus x when x minus 1 is less than 0, or we can say when x is less than 1. So we can say that f of x is uniquely defined real number for all x belongs to R, that is the set of real numbers. Hence, we can say that the domain of the real function f is R, that is the set of real numbers. Now we have to find the range of f. Now f of x is given as mod of x minus 1, and mod of x minus 1 is always greater than or equal to 0. Therefore, f of x is always greater than or equal to 0, and this is for all x belonging to the set of real numbers R. And since f of x is greater than or equal to 0, the range of the real function f is left closed right open interval 0 to infinity. And it is left closed because the 0 is included in this interval as f of x is greater than or equal to 0. So this completes the solution. In this question, a function f is given from R into R, which consists of the ordered pair x comma x square by 1 plus x square, such that x belongs to the set of real numbers R. You need to find the range of the function f. Let us begin the solution of this question. So here we have the given function. This can be written as f of x is equal to x square by 1 plus x square for all x belongs to R, that is the set of real numbers. Now, from this we can say that the given function f is uniquely determined real number for all x belonging to the set of real number R. We need to find the range of the function f for all x belongs to R. X square will be less than 1 plus x square. This implies x square by 1 plus x square is less than 1, which further implies that f of x is less than 1 because x square by 1 plus x square is nothing but f of x. Let us name this as 1. Also, x square is greater than or equal to 0. So this implies that x square by x square plus 1 is also greater than or equal to 0. Therefore, we can write f of x is greater than or equal to 0 because x square by x square plus 1 is nothing but f of x. So we name this as 2. So from 1 and 2 we have 0 less than or equal to f of x, less than 1. Hence, the range of the function f is left closed right open interval from 0 to 1. So this completes the solution. In this question, two functions f and g are defined from R into R. The function f is given by f of x is equal to x plus 1 and the function g is given by g of x is equal to 2x minus 3. We need to find out f plus g, f minus g and f by g. Let's begin the solution of this question. Here we have the two functions f of x and g of x. Now the domain of the two functions f and g is given as R. Because f and g are uniquely defined real numbers for all x belongs to the set of real number R. Therefore, domain of f plus g and domain of f minus g is also R. That is the set of real numbers. Now we will find f plus g, f minus g and f by g. Now f plus g of x is equal to f of x plus g of x for all x belonging to R, and f of x is given by x plus 1 and g of x is given by 2x minus 3. So we have 3x minus 2 for all x belongs to R. Hence, f plus g of x is equal to 3x minus 2 for all x belonging to R. Now let us find f minus g. Now f minus g of x is equal to f of x minus g of x for all x belongs to R. Now f of x is x plus 1 and g of x is 2x minus 3. So we get x minus 2x plus 1 plus 3. So this is equal to minus x plus 4 for all x belongs to R. So we obtain f minus g of x is equal to minus x plus 4 for all x belonging to the set of real numbers R. Hence, f minus g of x is equal to minus x plus 4 or 4 minus x for all x belonging to the set of real numbers R. Now we need to find f by g. Now g of x is given by 2x minus 3. Now before finding out f by g of x, let us first find the domain of f by g of x. Now f by g of x is equal to f of x by g of x such that g of x is not equal to 0. So this implies 2x minus 3 is not equal to 0 or x is not equal to 3 by 2. Therefore, domain of f by g is R minus the set containing the element 3 by 2. Now, f by g of x is equal to f of x by g of x for all x belonging to R minus the set containing the element 3 by 2. Now this is equal to f of x is given by x plus 1 and g of x is given by 2x minus 3. For all x belonging to R minus the set containing the element 3 by 2. Hence, f by g of x is given by x plus 1 by 2x minus 3 for all x belonging to R minus the set containing the element 3 by 2. So this completes the solution of this question. In this question, we have a function from z to z defined by f of x is equal to ax plus b for some integers a and b. We need to find the values of a and b. Let us begin the solution of this question. Here we have the set of ordered pairs in the given function f. Now, f of x is given as ax plus b for some integers a and b. Here, this 1, 1 belongs to f. Therefore, we have 1 is equal to a into 1 plus b, or 1 is equal to a plus b. This we can write as a plus b is equal to 1. Let us name this equation as equation number 1. Also, we have the ordered pair 2, 3 belonging to f. Therefore, 3 will be equal to a into 2 plus b. This implies 2a plus b is equal to 3. Now let us name this equation as equation number 2. From equation number 1, we have b is equal to 1 minus a. Substituting the value of b in 2, we get 2a plus 1 minus a is equal to 3, or a is equal to 3 minus 1, that is equal to 2. Therefore, we obtain the value of a as 2. Therefore, from 1 we have b is equal to 1 minus a, that is equal to 1 minus 2, which is equal to minus 1. Therefore, we obtain b is equal to minus 1. Now, for a is equal to 2 and b is equal to minus 1, f of x will be equal to 2x minus 1. Now, let us verify whether the ordered pairs 0, minus 1 and minus 1, minus 3 are contained in f. Now, f of 0 is equal to 2 into 0 minus 1, that is equal to minus 1. So, this implies that 0, minus 1 belongs to f. Now, let us find out f of minus 1. f of minus 1 will be equal to 2 into minus 1 minus 1, that is equal to minus 2 minus 1, that is equal to minus 3. This implies minus 1, minus 3 also belongs to the function f. Therefore, the ordered pairs 0, minus 1 and minus 1, minus 3 are contained in f for a is equal to 2 and b is equal to minus 1. Hence, the value of a is 2 and value of b is minus 1. So, with this we complete the solution of this question. In this question, a relation R is given from n to n. It is defined by R is equal to a, b such that A and B both belong to N and A is equal to B square. You have to say whether the given statements are true. Also, you have to justify your answer. Let's begin the solution of this question. Here we have the relation R, which is given by A comma B, such that A and B both belong to the set of natural numbers N and A is equal to B square. Let us first consider the first statement which is given to us. It says A comma A belongs to R for all A belonging to N. Let's verify whether this is true or false. Now, if A comma A belongs to R for all A belonging to N, this implies that A is equal to A square, because we are given here that if A comma B belongs to R, then A and B belongs to N and A is equal to B square. So here we will have A is equal to A square. Or this can be written as A minus A square is equal to 0. So this implies A into 1 minus A is equal to 0. So this implies that A is equal to 0 or A is equal to 1. Now, A cannot be equal to 0, and this is because A belongs to the set of natural numbers N. So the only option left is A is equal to 1. So this means this given statement, it is true only for A is equal to 1. So we can say that the given statement is true only for the value of A is equal to 1. It is not true for all A belonging to the set of natural numbers N. Hence we can say that the given statement is not true. So this completes the first part. Now let us consider the second statement which is given to us. It says A comma B belongs to R. This implies B comma A also belongs to R. Let us assume that the ordered pair A comma B belonging to R implies that the ordered pair B comma A also belongs to R. This means A is equal to B square implies that B is equal to A square. And this means B is equal to A square. So in place of A square we can write B square whole square. So this means B is equal to A square. So in place of A square we can write B to the power of 4. And this implies B into 1 minus B cube is equal to 0. And this means B into 1 minus B into 1 plus B square is equal to 0. So the only real values possible are B is equal to 0 and B is equal to 1. But B is not equal to 0, because we know that A and B belong to the set of natural numbers N. Therefore, the only possible value is B is equal to 1. Therefore, A is equal to B is equal to 1. Therefore, the given relation is true only for A is equal to B is equal to 1. It is not true for all values of A and B belonging to the set of natural numbers N. Hence, we can say that the given statement is not true. Next, let us consider the third statement. And let us see whether this is true. It is given that if A comma B belongs to R and B comma C also belongs to R, this implies that A comma C also belongs to R. Now A comma B belongs to R. This implies that A is equal to B square. So let us name this as 1. And B comma C belongs to R. This will imply B is equal to C square. And let us name this as 2. Now from 1 and 2, we have A is equal to C square whole square, which implies A is equal to C to the power of 4. Now, if A comma C belongs to R, we must have A is equal to C square. So let us name this as 3 and this as 4. So from 3 and 4 we have C square is equal to C to the power of 4, or C square minus C to the power of 4 is equal to 0, or C square into 1 minus C square is equal to 0, and this can be written as C square into 1 minus C into 1 plus C is equal to 0. So this implies C is equal to 0, or C is equal to 1, or C is equal to minus 1. Now we know that C belongs to the set of natural numbers n. So C cannot be equal to 0 and C cannot be equal to minus 1. So we obtain C is not equal to 0 and C is not equal to minus 1. Therefore, the only possible value of C is 1. Now we have B is equal to C square and A is equal to B square. This means that A also is equal to 1 and B is also equal to 1. Therefore, the given statement is true only for A is equal to B is equal to C is equal to 1 and not for all A, B, C belonging to the set of natural numbers n. Hence, we can conclude that the given statement is not true. So with this we come to the end of the solution of this question. In this question, two sets A and B are given. Also, a set of ordered pairs F is given. You have to say whether the given statements are true or false. Let's begin the solution of this question. Here we have the given sets A and B, and here we have the set of ordered pairs F. Let us first list the elements of the Cartesian product A cross B. So here we have the ordered pairs of the Cartesian product A cross B. Now, for this F to be a relation from A to B, it has to be a subset of this Cartesian product A cross B. Now we can see that all the elements of F are also elements of the Cartesian product A cross B. Here we have 1, 5. It is also present in A cross B. Then we have 2, 9. This is also present in A cross B. Then we have 3, 1. Let us see if it is present in A cross B. Yes, it is present in A cross B. Then we have 4, 5. This is also present in A cross B. And finally, we have 2, 11. Let us check whether this is present in A cross B. 2, 11 is also present in A cross B. So we can say, since all the elements of the set of ordered pairs F are also present in the Cartesian product of A cross B, F is a subset of A cross B. Therefore, we can say that F is a relation from A to B. That means this first statement that f is a relation from A to B is true. Hence, the given statement that f is a relation from A to B is true. Now we have to say whether f is a function from A to B. Now we know that a relation R is a function if no two ordered pairs have the same first element. So now let us observe the set of ordered pairs in F. Here you can see that 2, 9 and 2, 11 have the same first element 2. So 2, 11 and the ordered pair 2, 9 have the same first element 2. Therefore, f is not a function from set A to set B. Hence, we can say that the given statement, that is, f is a function from A to B, is false. So with this we conclude the given question. In this question, it is given that f is equal to the set of ordered pairs AB, A plus B such that AB belongs to Z. It is also given that the f is a subset of the Cartesian product Z cross Z. You have to say if f is a function from Z cross Z. Also, you have to justify the answer given by you. Let's begin the solution of this question. Here we have the set of ordered pairs f given by AB, A plus B such that A and B both belong to the set of integers Z. So let us now verify whether f is a function from Z to Z. Let us take the value of A as -1 and value of B as -2. Then we have AB is equal to -1 into -2, that is equal to 2. Also, we have A plus B is equal to -1 plus -2, which is equal to -3. Therefore, the ordered pair 2, -3 belongs to F. Now let us take A is equal to 1 and B is equal to 2. Therefore, we will have AB is equal to 1 into 2, that is equal to 2, and A plus B will be equal to 1 plus 2, that is equal to 3. Therefore, 2, 3 belongs to F. Now you can observe that this 2, -3 and 2, 3 both are belonging to F and both have the same first element as 2. So we observe that the ordered pairs 2, 3 and 2, -3 both are present in F having the same first element 2. And since we know that in a function no two ordered pairs have the same first element, f is not a function. Hence, the given set of ordered pairs f is not a function. So this completes the solution. In this question, a set A is given to us and f is defined from set A to the set of natural numbers n by f of n is equal to the highest prime factor of n. You need to find the range of f. Let's begin the solution of this question. Here we have the set A which is given to us, and f is defined from the set A to the set of natural numbers n such that f of n is equal to the highest prime factor of n. So first let us find out f of 9. For that we need to know the prime factors of 9. The prime factor of 9 is 3, because 3 is the only prime factor of 9. Therefore, f of 9 will be equal to 3. Next we have to find f of 10. And the prime factors of 10 are 2 and 5. So 5 is the highest prime factor of 10. So we write the highest prime factor of 10 is 5. Therefore, f of 10 will be equal to 5. Now let us find out f of 11. And the prime factors of 11, there is only one prime factor of 11. So we write the prime factor of 11 is 11 itself. So it is the highest prime factor of 11. So f of 11 will be 11 itself. Next we need to find f of 12. And the prime factors of 12 are 2 and 3. And of course 3 is the highest prime factor. So we write the highest prime factor of 12 is 3. Therefore, f of 12 is equal to 3. And finally, we have to find f of 13. The factors or the prime factors we say prime factor because there is only one prime factor of 13, that is 13 itself. So the prime factor of 13 is 13. So naturally that has to be the highest prime factor. Therefore, f of 13 will be equal to 13 itself. So here we have f in roster form, and we are asked to find the range of f. And as we know, range is the set of second elements of the set of ordered pairs. So we can list down the elements of the range of f. So we have 3, 5, 11 and 13. Thus we obtain the range of f. So with this we come to the end of the solution of this question.